Welcome everyone to one of our live sessions for the Astronomy State of the Art course. We've been talking about stars. This week's subject is stars, but we'll also, a lot of interest generated by exoplanets, of course, one of the hottest fields in science, really. And so our subject matter today can span exoplanets and stars. So happy to take any of your questions. Some great questions have been on Udemy's site already. I think I've caught up with most of them. But happy to take more right now.
Okay, so the first question, let's see, we have one that's ready. So first one is related to your work with Buddhist monks. What was it like working with the Buddhist monks?
Okay, something completely different, which is what that experience was. The short background is that I got a call out of the blue 5 years ago from a young postdoc at Berkeley who is the organizer of a program called Science for Monks. The Dalai Lama decided a decade ago that his Buddhist monks needed to be trained for the 21st century, and that involved learning math and science, which is not a standard part of their curriculum. And so the program started to bring out Western teachers for workshops 3 or 4 weeks long to pretty remote parts of northern India where the monks live in monasteries near Dharamsala, which is the government in exile location for the Tibetans in India. And I became one of the teachers teaching cosmology, and other people were teaching biology, math, physics, and neuroscience. And it's an amazing experience, of course. It's a very isolated situation, pretty much living in a monastery with not too much creature comforts, not really hot water, electricity occasionally. It's pretty primitive, but it's an amazing experience. And the Buddhist monks are extraordinary students. They have phenomenal powers of discipline and application. They've been studying for a decade or more in their own tradition, and they're hungry for science. They want to know what science is learning about the universe and the natural world, because they also take biology. And so, I've got to know some of them over the years. Language is an issue. Their English is modest. My Tibetan is almost non-existent. I can say very few words. But we managed to communicate anyway. And I've been pretty much every year since 2008. And I'm going back, I think, late this year.
All right, so the second question is from Errol Swanpool, and he asks, says, we humans are so darn clever, we even know how stars are born. Why then can't we plunk some dust and stuff in a bowl, spray some hydrogen and helium over it, mix it together, spin it around, and whack a new star into existence? It's tongue-in-cheek, but seriously, why can't we?
Right. Now, that's a great question, and a sign of our modest technology. We've only had, well, let's say high technology for perhaps a century, 2 centuries since the Industrial Revolution. Simulating a star is extraordinarily difficult. So the stars manage the trick of fusion of hydrogen into helium by the fact of aggregating a huge amount of material, a star's worth of material, into one region of space, and basically gravity just does the rest. And it's effortless for a star because gravity is the cause of the pressure and the heat and the density that makes fusion occur naturally in the center of a star like the Sun or any star. If we want to simulate that process on Earth, we don't do it using gravity. We don't have the benefit of gravity at all. We have to do it by brute force. And the brute force involved is the brute force involved in creating a condition of basically 10 million degrees Kelvin in a small region of space. Now that's an immediate problem because any material substance we can make, the most powerful metals or alloys we know, melt at the temperatures of a few thousand degrees. And so there's nothing that can contain 10 million Kelvin plasma. The only way it can be contained is a magnetic bottle. And that's part of why fusion on Earth has been such a difficult thing. Starting in the 1960s and 70s with the tokamak technology, the Americans and Russians have been attempting to create fusion process in a controlled situation on the Earth, and it's exceptionally hard to have a plasma. magnetic field, the plasma itself is magnetized, and it becomes unstable, it oscillates, it escapes from your containment mechanism. And this has been decades of arduous work just to even get that technology working. It's 40 years old. Meanwhile, we have new facilities, laser ignition facilities at Los Alamos and Livermore and some of the national labs in the US, and also one in Japan and one in Europe, that are trying a somewhat different approach. They're focusing a set of lasers on a small region of space with a pellet of hydrogen, or actually deuterium, trying to get fusion occurring in that tiny space by having high-powered lasers focusing on it. And the result of all this work is that for tiny fractions of a second, milliseconds really, or maybe less, we can simulate the conditions at the center of a star, and some tiny little dribbling amounts of fusion occur momentarily. And that's it. It's not a self-sustaining reaction. It's not a reaction that generates anything like the energy that was produced, that was required to set up those physical conditions. So we are, somewhat discouragingly, still very, very far from having a sustainable fusion reaction on the Earth. We still think it's worth all that huge technological effort because energy is a big problem for us. We're still subsisting essentially, for the most part, on fossil fuels that only have longevity of decades or maybe 100 years or so. We haven't got sustainable alternative energy. And fusion is, of course, a clean process that doesn't generate radioactive byproducts. The only waste product is heat itself. So there's plenty of reason to want fusion to work, but the technologies required are indeed intimidating. And we have got closer over those decades, but we're not there yet, not even close. If you consider a microsecond of fusion at a cost of 100 times more energy than you got out getting close, then, well, we've made some progress.
Alice Amanda Kay wanted to know if you had a simple analogy to explain the Higgs boson.
Higgs boson was a great discovery of physics basically over the last couple of years. It took 2 years of data from the Large Hadron Collider at CERN to cement the discovery at a level that physicists all believe. It's a quite subtle and esoteric mechanism. The basis for the Higgs is the fact that we have all these fundamental particles. We have quarks, we have leptons or light particles, mesons, we have neutrinos, we have different flavors or families of these particles, 3 different families, and they all have particular energies or masses. And the theory of particle physics, the so-called Standard Model, it tells us nothing about why there are these multiple families of particles, like quarks and leptons, or why those particles have the masses or energies that they do. It's essentially a mystery in the Standard Model. It's particle, which it's really not a particle. The Higgs is more of a field, what physicists would call a field, is the mechanism by which all of those particles attain their mass. The best analogy I've seen anywhere is the one where you have a room full of people, and the people in the room represent the fields that permeate space. So space is permeated by fields of various kinds. There's electromagnetic fields, there's the field of the actual vacuum itself, which has a 0 order vacuum energy, a half h nu, that's part of quantum theory. And in the modern theory of particle physics, the vacuum is pervaded by the Higgs field. And the Higgs field is like this ocean, this sea of people in a room. And then as an interesting person arrives at one end of the room, the people in the room aggregate towards them and move towards them wanting to talk or look or whatever. And as that person moves across the room, the people in the room, who are always present in the room, interacting with this celebrity or this interesting person, sort of slow that person down and create a wake, if you like, through the room. And so that's the analogy, the sort of cocktail party analogy I've heard it called, where the Higgs field, something permeating space, interacts with things that we call particles to give them their mass. And I suppose if you wanted to push almost to the breaking point the analogy, the more interesting or exotic the celebrity that walks through the room, the more people glom onto them or ask them questions or try to crowd next to them, and so the more mass they have. The more exciting the celebrity, the higher the mass. And so that's a general description of how the mass could vary from some basic attribute called the Higgs field. So the Higgs field is just that. It's a mechanism and a field permeating space that gives particles their mass. Now, an important thing that hasn't been said, or that isn't demonstrated by the detection of a Higgs field or particle, is why the particles that we have, the quarks, the leptons, the neutrinos, have the exact masses they do. So we have a mechanism for providing particles with mass, but we still don't have a deeper explanation for why nature has arranged it so that there are 3 generations of quarks and 3 generations of leptons. That's still something we don't understand.
Okay, our next question is from Pete Hermes. Given present science and observational capability, what are 1 or 2 of the more significant items we are likely to learn, obtain, or how will we otherwise expand our understanding of the universe from the next supernova event if it should occur within the next 10 years?
Good question about supernovae, because we're due. It's hard, you can't predict. These are not random events, but they're statistically rare, and so we can't predict when a supernova will go off. So and the question alludes in part to the fact that within the Milky Way, we're long overdue for a supernova to go off. The last one was 1604, Kepler supernova. That's over 4 centuries, and the mean frequency of supernovae within a galaxy of our size, with the number of stars it has, is about 1 a century. So we're clearly overdue, but the statistics are governed by Poisson law statistics, which means that doesn't mean something's wrong with our theory of stars. If you wait 4 centuries, it can happen. It's possible. Poisson statistics govern the time of arrival of a bus. If you're in a situation, an inner city situation where these buses are supposed to arrive during rush hour every 10 minutes, it can happen that they bunch up, and just for fluctuations in statistics and traffic flow issues, you could wait 40 minutes for a bus. You wouldn't think the buses had stopped running or they'd all broken. So we're due. What would we learn if a supernova went off in our galaxy? Well, first we'd have to be careful of what we wish for, because if the supernova was really close, we'd all be in trouble. That has to be, however, within 10 or 20 light years, and that's a very tiny fraction of the Milky Way. So the odds of a supernova going off close enough to us to be hazardous are exceptionally low. So let's just not worry about that right now. If we get a supernova at a more plausible distance of a few thousand light years, so significant distance within the galaxy, but maybe not on the far side, where it might actually be hard to observe, we would have such an amazing array of large telescopes to point at the supernova that we'd get exquisite detail on what was going on inside that detonating star. Now, the really interesting thing would be that we have neutrino detectors now. And the neutrinos, if you've listened to the podcast with Dave Arnett, who's really one of the world's experts on supernovas, so I was very lucky to be able to interview him. He's a fellow of the Academy. I didn't reel off a list of his achievements and awards in my interview with him, but he is an extremely highly reputed researcher on supernovae. Part of his work involved showing that the neutrinos from the supernova, just due to intense particle interactions, which generate as many or more neutrinos as photons, the neutrinos leave quicker than the light and the radiation. We saw this in supernova 1987A, the last time we got a supernova bright enough to observe easily, but not in our galaxy. That was 60,000 light years away in the Magellanic Cloud. So because we have neutrino detectors, and they're working continuously, the first signature of a supernova will not be anything we see with telescopes or with the naked eye. It will be the pulse of neutrinos arriving at these neutrino detectors. And that's really important, because that's the first information that can come out. That information alone, the neutrinos that come out of the supernova, will give us an enormous new insight on the nuclear physics in the detonation zone, and maybe even teach us something about neutrinos themselves. 1987A was the first supernova in the era of neutrino detection, and I think the number of neutrino events was 6 or 7. It was just a tiny handful, enough to say that it happened when the supernova went off, but that was all. If we get a big beefy supernova within 100 or a few hundred or a few thousand light years will detect hundreds of thousands of neutrinos from it to actually do very interesting astrophysics with the neutrinos themselves. The neutrino signature or signal will be the alert that the astronomers need with all their telescopes to point in the sky to that region of space. And so everyone will be on it. Probably every major telescope that can observe will be diverted from their normal science unless they're doing some other time critical work. And so everyone will be targeted on the supernova. Now, if it's fairly close, ironically, there may be actually too much light for some telescopes to observe it. It would basically saturate the detectors. The CCDs can only hold a few 100,000 electrons in their wells, and if you read them out too rapidly, like once every second or so, you're spending 30 seconds reading out the detector for 1 second of gathering data. So operationally, you have a problem when a source is too bright because it's actually hard to gather the data or the instrument saturates. So some telescopes may have this problem, and in fact, some of the big telescopes may have their apertures stopped down. Their shutters may be partially closed just to stop them from being blinded. But if we throw the full array of all our capabilities across the electromagnetic spectrum, we are going to learn more from the next supernova in our galaxy than we've learned from the sum of all supernova observations up to this point. We will refine the models of the detonation, of the core collapse, these amazing sequences of events that take place actually in less than a second that lead to the propulsive explosive force that gives us a pretty light show in the sky. But that's much later. The supernova remnant is what happens hundreds or thousands or tens of thousands of years later. And of course, we would get to watch that play out over the subsequent decades. But I think what people are excited about is that with the neutrinos as the alert and all the telescopes in the world that can do it, pointing at the light as it peaks, we're going to learn an enormous amount about these exotic regions inside a star. I don't know that we can use those observations to decide in a particular case whether a neutron star or a black hole had been created. There's not an obvious telltale of that. But we're still going to learn an enormous amount about these supernovae. And we're going to constrain models and simulations that are done with computers now, which are somewhat speculative because we just don't have enough input physics.
David Jeffers wanted to know, when they determine the age of rocks on planets, how do they know it's not ejected star matter that they are determining the age of?
So when we measure the age of rocks, it actually is not possible to do that very accurately remotely. So if we're I'll talk about this in a couple of aspects. For a planetary surface that we observe even with a rover or a satellite, an orbiting satellite, our measurement of the age of rocks is very intimate. The classic way of measuring the age of surfaces, or rocks if you like, on Mars and the Moon and Mercury is by crater counting. And that barely constrains the ages within an accuracy of 100 million years or a few 100 million years. That's pretty crude determination. To go much better than that, essentially, we have to have the material in our hands. We have to look at the radioactive isotopes that occur naturally in rock and use the relative amounts of those isotopes, the parent isotopes that are heavy elements and the daughter isotopes that they decay into, and the relative amounts of those give us a time curve, essentially, for the rocky material and say how long it was since it formed. And we've only been able to do that for rocks that we have from, of course, the Earth, which is why the age of the Earth is very well determined to 3 decimal places, the Moon, where we have actual rocks back from the Apollo missions, and Mars, where we have Martian meteorites. You've probably read recently about the possible discovery of a Mercury meteorite, and people have argued about this in the past, whether we happen to have free samples of other bodies in the solar system. It's been very hard to be sure of that. But for all those rocks, we can use these standard radioactive isotope methods to measure the age with quite high precision, at least 1%. And all of those ages, when they're measured, are certainly consistent with our age for the solar system. For example, the Allen Hills meteorite, which you may have heard about from the mid-1990s when there were claims of fossilized life in it, that was well measured to have an age of 3.6 billion years from these radioactive isotope methods.
Okay, the next question is from Dixie Burns, and she says that last month Harvard-Smithsonian announced a new type of supernova, 1AX, and she wants to know if that is going to cause any challenges with the standard candle distance measures.
Yeah, that's a really good question, and I'll just back up to what the context for this is. There are now a number of subtypes of supernovae, and I, taking a high-level view of the subject, I didn't get into the details of the subclassification. In general terms, the two fundamental different types of supernovae are the single isolated massive stars collapsing, the type 2s, and then the supernovae that go off in binary systems. The supernovae that go off in binary systems are incredibly useful for cosmology, and we'll be talking about this in a week or so. Because a white dwarf is essentially tilted over the mass limit at which it detonates as a supernova in a very regulated way by mass transfer from a binary companion. And what that means is it's a sort of well-calibrated bomb, and therefore light bulb. And that's extremely useful because the luminosity of what were traditionally called supernova 1As, these binary system detonating supernovae, the luminosity, the number of photons coming out of that explosive event, was observed to be uniform to about 15%. So wherever they occurred in the universe or in cosmic time, if we understand that they have this mean luminosity, or number of photons being emitted, we can use how bright they appear to be to say how far away they are. So it's a distance measurement. And it's very hard to get distance measurements beyond a few billion light years. And supernovae have been the best way to do that for the last couple of decades, actually. Now that method, of course, makes a very, very critical assumption. It makes the assumption that the supernovae are all this very regulated type, where the explosion occurs in a well-understood way in a binary system, and that also that the fundamental nature of the explosion is the same. The physics of it is the same. And when you get into the details, or the weeds even, it turns out that the chemical composition of the star, or the remnant that explodes, can affect its brightness. So we actually are assuming, in using supernovae as distance indicators and doing cosmology with them, that a supernova, a type 1 supernova, 1A, the supernova that goes off 8 billion light years away, and of course 8 billion years ago, when the universe was a somewhat different place, is fundamentally the same and physically the same as a supernova that goes off in the nearby universe. This discovery out of Harvard-Smithsonian of a subclass of type 1s that has somewhat different spectral properties and perhaps kinetic and energetic properties is at the very least a fly in the ointment, and maybe a shadow over the use of this method. Because if we find subclasses of the binary supernova detonations that don't have the same fundamental properties, then we could be misinterpreting what's happening in the distant universe. It's such a recent discovery that it's not clear that that's the case, but just the fact that we are finding variations in the type 1A class, that it has subcategories that might be physically different, is a cause of concern to cosmologists. Remember that dark energy, the entire implication of the existence of dark energy, was originated from the observation of supernovae and still has as its only direct piece of evidence the observation of distant supernovae. So the stakes are very high in this field, since dark energy, the biggest component of the universe, hinges on the use of supernovae in this way.
All right, so our next question. Why is the emission from a pulsar directional and not omnidirectional?
So that's a good question. Pulsars are, part of the answer is that pulsars are collapsed stars, so they sort of share the properties of the sun, except in a situation where the material has collapsed to an incredibly dense state. So two corollaries of that collapse are that the rotation rate, of course, is incredibly fast. So something like the sun, rotating about once a day, is collapsing by a factor of 1,000,000 and spinning 1,000,000 times faster, so it can spin in a second or less. The other thing is that the stars, like the sun and really any star, has a magnetic field, and the magnetic field is also squeezed, essentially, because it's trapped in the plasma of the star. So when the star collapses in its phase of evolution to become a neutron star, that magnetic field is also squeezed. So you're dealing with a situation in a neutron star where you've collapsed a star to nuclear matter densities where the rotation is incredibly rapid and where there's an entrained or trapped magnetic field. So the first answer to the question is that the magnetic field itself, the fact that it's a dipole field, provides a mechanism whereby the two poles of the star can potentially have emission that the rest of the star, the equatorial regions or the other latitudes of the star, don't have. And that emission will typically be cyclotron emission, because electrons will be spiraling in the magnetic field. Interestingly, it's still a cold situation. The star is cold because there's no nuclear energy. And so when electrons move in magnetic field lines, but they're not highly relativistic, the emission is called cyclotron emission. When it's relativistic, it's called synchrotron. They're different mechanisms. So that cyclotron emission, which is, because it's low temperature, is also low energy, meaning radio emission, is the mechanism by which pulsars were discovered. So really the reason that the radio emission doesn't come out everywhere is partly tied to the fact that you have a star with a magnetic field and the energy is created preferentially on the poles. But it's more complicated than that, because the neutron star is not a uniform, pristine object. It actually has a crust, and the crust has structure, and the structure changes. This is a mechanical object. It's an atomic nucleus the size of a city that's spinning, hundreds of times an hour, and it has mechanical stresses. And so the neutron crust actually has fractures, fissures, it rearranges in starquakes, and the things that happen in the neutron crust can also generate emission, where energy is released as the star reconfigures its neutron crust. And so some of the exotic phenomena that have been observed in pulsars, and radio emission again, occur because the crust is doing strange things. It's glitching, and the frequency of the pulsar shows these glitches or starquakes. And that also is quite specifically tied to places on the surface where the star is rearranging. So people have now gone from just thinking that that might happen to actually studying that. There are dozens of pulsars where starquakes have been observed or inferred, and they're always associated with particular places on the neutron star surface.
Okay. Our next question, Julian asks, I've heard of black holes with hair and black holes with no hair. Do you know what this refers to?
Yes, the supposition of black holes, the theory, first of all, of black holes originates with general relativity, of course. They're a prediction, a consequence of general relativity. The mature theory of black holes dates to the 1960s and 1970s, and famously, of course, Stephen Hawking came up with many of the current ideas of black holes, not all of which have been tested. It seemed that for a while that black holes were extraordinarily simple objects, but really that only had three attributes. They had a mass, they had a spin, and so an angular momentum, and they could potentially have a charge, but that's been argumentative. So the fact that black holes are incredibly simple physically is a supposition that led to the idea that they have no hair. Hair meaning the idea that the hair is the external part of the object that tells you something about what's inside it. And the black hole has nothing external to it. It's an event horizon which seals off information. And all you really can measure from the outside is the spin and the mass. Whether black holes have hair or not means whether there are other signatures from the black hole in its immediate vicinity that can give you extra information about what went on in the black hole. And people have essentially argued about this. So the no-hair theorem of black holes says that no, it's really as simple as we thought. The black holes have two basic properties, and that's all you can measure or infer or determine. Well, Hawking put the first little chink in the armor of this idea because he came up with the idea of Hawking radiation. This is in the mid to late 1970s. Hawking radiation is the fact that as particles are near the event horizon, or in a situation where you imagine near the event horizon particle-antiparticle pairs are created, which can happen from pure energy, and it happens spontaneously in the vacuum of space, so there's no reason it can't happen near a black hole. You can imagine quite easily a situation where in the spontaneous creation at the event horizon or very near it of a particle and an antiparticle, because of the conservation of energy and momentum, one of those pair will go into the event horizon and be lost from the universe, and the other will emerge to be observable. And that was a logical physical possibility that Hawking came up with. And when he followed through the calculation, he realized that this is a mechanism whereby energy and actually mass can escape from a black hole, mass and energy being equivalent, 3 equals mc squared. So Hawking radiation itself is a form of hair that a black hole has. And in Hawking's theory, Hawking radiation means that a black hole has a temperature as well as a mass and an angular momentum. And the theory allows you to calculate the temperature of a black hole. It's a very, very low temperature. These are intensely cold situations, which operationally means that the rate at which the black hole is bleeding or losing mass is very, very slow. But you can calculate this rate, and this leads in turn to the idea that black holes are slowly evaporating. So once you form a black hole, the things that are inside the event horizon are lost from view, lost from communication with the outside universe, but the black hole itself is evaporating slowly. Now for a black hole like the sun, or something more massive than the sun, a normal massive star dying, the time scale for Hawking radiation to evaporate the entire black hole is, I can't even remember the exact number, it's like 10 to the 50 years. It's just a crazy long amount of time. But in nature, it's possible that lower mass black holes are made, and those lower mass black holes evaporate quicker. In fact, if you watched a normal stellar mass black hole evaporate, it would evaporate in that phenomenally slow way. And then as it evaporated down to a small object the size of a house or a brick or a particle, it would be a crescendo of evaporation until it just fizzled away and disappeared quickly. The supermassive black holes at the center of galaxies correspondingly evaporate at an even slower rate, and that they are essentially eternal as far as we can tell. So the hair of a black hole is partly its Hawking radiation. That is part of the standard theory of black holes, in fact. So black holes do have hair, and they do have that third property of temperature. Although, to be correct, it's never been literally observed. So the experimental verification of Hawking radiation has not yet happened. People have continued to work on the theory of black holes, and another idea that you may have heard of, and maybe part of the reason for the question, is the holographic principle. So people have worried that black holes lose information from the universe. A black hole has an enormous amount of entropy or disorder, which in a physics terms is a way of saying the number of equivalent physical states to what's going on inside a black hole is huge. Because if you think about it, a black hole is mute to whatever went into it to make it up. You could have a black hole that's just the compressed late stage of a star, or you could somehow take a lot of space rocks and squeeze them together artificially into some region of space, or you could take encyclopedias or books or barnyard animals. You could take anything you want, and in principle, if you could squeeze it enough, you'd make a black hole. And the black hole you got would tell you nothing about what it went into it, what made it up. And for physicists thinking about this, this became the information paradox. How can that be that information is lost so irretrievably into these regions of space? So another form of hair, if you like, on the black hole is the idea of the holographic principle, which is that somehow in the event horizon is coded in a way that the theory describes, but not, completely, information on what went into it, that it's not completely lost. Now, it's not is literal as a hologram, where a hologram in optics really contains the information of the view that was recorded in the hologram. So you're essentially recreating a three-dimensional picture of a view that went into making the hologram. Hawking has a nice analogy for this. He says, well, the preservation of information in the event horizon is not like the encyclopedia pages just being recorded neatly in the event horizon. It's more like the encyclopedia was burned because creating a black hole was a messy business, and you're looking at the ash from the encyclopedia in the event horizon, which has some fraction or some fragments of the information of how the black hole was created. But that the event horizon could contain any information at all that might somehow be decodable by us is an extraordinary idea, and that's the holographic principle. It is unverified. It's a part of its somewhat speculative black hole theory that we actually haven't even figured out a way to test. But it's another form of hair that a black hole might have, where everything that went into the black hole is not irretrievably and interminably lost.
All right. So back to Dixie's question about this new kind of supernova.
Mm-hmm.
What is the proposed explanation as to how the white dwarf in this new kind of supernova survives, whereas in supernova types 1A, it does not?
I've only read one story on this, so I'm actually probably going to punt this question until I read the research article that the discovery was based on. So I don't think at the moment that we know what was the evolutionary path that led to this situation. The white dwarf, once a white dwarf passes the Chandrasekhar limit, it's the point of no return. So at that point, the detonation occurs, the collapse leaves behind a compact object like a neutron star or a black hole, depending on the mass that was reached. So actually, at this point, the jury is out on what the evolutionary path of this new system was. It's too recent a discovery to know.
We had a couple of people who are interested in using so this change of topic a little bit, using the Teach Astronomy website with their classes. And I was just wondering if you could talk for a minute about Teach Astronomy as a resource and who can use it and how it's available.
Sure. Yes, some people have been interested, and I encourage, of course, everyone to go there. It's a free and open site. There's no everything that you see there you can always use, and it's pretty robust as far as being up most of the time, because we do already have some classes around the country that are using it as essentially a textbook. So the key resource for people who teach is the equivalent of an online textbook. If you've taken an astronomy class as a university student or taught one as a professor, you know that astronomy textbooks are now $120, $140, kind of crazy amount of money. I used to write textbooks myself, so I was part of the problem, I guess, at that point. So what we have is the equivalent of an online book, which is one book that I wrote a while ago that was maintained and updated and aggregated into a set of 400 or so articles with images inserted that had no copyright restriction, because most of the images in the textbook are also copyright as well as the text. So that's a primary resource that is useful for an instructor who wants to save their student money. The average college student in the U.S. spends $1,000 a year on textbooks. I have 2 kids in college, actually only one now, and so I pay those bills every semester, so I know exactly what that feels like. And so you can't be free, and it doesn't maybe have as many of the bells and whistles as some of the current textbooks do. It doesn't have as many of the ancillary materials and the freebies that they throw in to instructors, especially to get them to adopt the book, but I think it's got all the basic information. And then it's allied to a set of image resources where we've got all the astronomy picture of the day in a astronomy picture of the day. Is a phenomenal resource, of course, that is open to anyone from that website, but it's not organized in any very useful way because they're sequential, each different topic, and you can search by topic, but we have it clustered so that if you're interested in Mars or interested in Jupiter or spiral galaxies or whatever, you can very quickly and easily find all the astronomy picture of the day images out of essentially 8,000 or 9,000 now in the archive that relate to that, and their captions. The captions are also very useful, full of information. And then we've added to that a resource called AstroPix, which comes out of NASA JPL. And it's essentially a growing amount of the great observatory images, which is to say Hubble, Spitzer, and Chandra, with very detailed captions and actually more detailed information on how the images were taken, with what telescope and field of view and filter and integration time and so on. So work that you can actually use for projects. And the similar about 1,200 165 days, which are also, I've done a couple myself, which are also searchable in that way. So it's useful. It's a loosely organized teaching resource, which is to say there's no curriculum attached. There's no indication of topics week by week of how you should teach a class, because it's really there also for people such as you taking this course to just use as a resource. You just want to dip in and dip out. See something about Titan, or go in and see what's going on with black holes or active galaxies, then you can look at that information. So I, of course, encourage everyone to explore that resource and give us suggestions. There's a feedback button right at the top of the home page on how we might improve it, or resources that we're missing that we could add. And the final comment, which gets into areas like controversy in academia, we also included in that resource the astronomy content in Wikipedia. Wikipedia is more controversial in academia in subjects other than mine. In our group and myself personally, I've read probably 170 or 180 Wikipedia articles on astronomy topics, and they're very good, actually. Their head-to-heads have been done with online encyclopedias, and in science topics, it's hard to find major errors in Wikipedia. There's no issues of point of view or controversial subject matter that afflict political articles in Wikipedia, for instance. And Wikipedia content's really good, and they're very well built out, and of course they're extremely current. When something happens with one of the Mars rovers or a space mission, it's pretty much built in and edited in Wikipedia that day or within a few days. And of course you can go to Wikipedia, as people do all the time, and search on a particular topic. But what we've done is create a walled garden where we, with a clever algorithm, filtered out the roughly 40,000 articles among the 4 million on Wikipedia that were astronomy, and just segregated those off into an area of a database. And then we clustered that database based on keywords in the text of all those articles, so that from a starting point of an article, say on spiral galaxies, you can surf in the little Wikimap visual display we have to all the related topics like dark matter or particular spiral galaxies or stellar populations and so on. So we sort of tamed the vastness of Wikipedia by peeling off the astronomy part, a highly non-trivial number of 40,000 articles. And then we've organized it in this dynamic way by doing clustering of the content. So you don't necessarily have to know everything that's in there or out there, because you will encounter it from a starting point of a keyword search. You should encounter it very easily just by surfing adjacent links.
Paul O'Neill wanted to know what your thoughts were on extraterrestrial life other than carbon-based life forms.
Non-carbon-based life, an interesting question, and science fiction writers, they've speculated about this for half a century probably. I think I've talked to a chemist on this. Steve Benner is a physical chemist at the University of Florida, very highly reputed researcher who's actually altered the toolkit of life. He's actually altered some of the base pairs of DNA and tried to create alternative genetic material. So he's done some very radical experiments like that. But as a physical chemist, he's probably the best person I could have ever asked about, okay, what's the deal on silicon-based life? It's in the same column of the periodic table, which means it has similar electronic and reactive properties could you just swap out silicon for carbon, or could you have a different chemical basis for life? And he gives a measured answer, and he just says probably not. He just says it's not as good. So just to, I realize I realize non-carbon doesn't just mean silicon, but let's just deal with silicon first, because silicon has fairly high cosmic abundance and has similar chemical potential properties in a complex situation. The answer to a chemist is that it's not nearly as good as carbon. Form complex molecules with carbon, they're neither as diverse nor as stable in a biochemical setting as carbon-based chemistry. And so on a number of grounds chemically, even if you had silicon as a basis, and there was plenty of silicon in your environment, you're unlikely to generate the level of complexity that was required for life to form, for us to go to the level of a first cell. So to a chemist or to a biochemist, silicon just isn't nearly as good. The other part of the answer is that carbon's there. Carbon is one of the most abundant atoms in the universe, produced in the center of stars and distributed into space, and part of the debris. When stars form, it's part of the debris that will form planets. So carbon or organic material is going to be there, and it's going to be in many different environments. So when you're thinking of alternative biology, it's certainly possible, but the carbon is there. The carbon is infinite in its chemical possibilities because of the ability to form long and essentially endless chains and loops. And so you don't sort of need to look beyond carbon. The other standard way of speculating about life beyond carbon is to say that maybe it's happening in a completely different way. Fred Hoyle wrote a great science fiction book, The Black Cloud, in 1957, I think. And he speculated about life forming in an interstellar molecular cloud where you already have amino acids in deep space. They don't have to be on the surfaces of rocks or on planets. And so maybe with much slower interactions that would occur in a liquid, in a gas, over plenty of time you have, 13 billion years since the universe started, maybe you can form complex molecules in a gaseous situation. So that would be a highly radical form of biology based on a gaseous environment rather than a liquid and solid environment. And nobody has come close to being able to simulate how that would happen in a lab, and the theory of how it would happen makes it seem rather implausible. So I think scientists have tried to take seriously the possibility of non-carbon-based life. And when they've explored it in detail, as with silicon, and maybe to a lesser extent with gas-based life, they found that it just either doesn't work or doesn't work nearly as well as carbon-based chemistry. So I think we're expecting that organic material will be the basis of biology wherever we find it.
All right, one more question about wavelengths of light that penetrate the atmosphere.
Mm-hmm.
One of the students is asking how or why is it that that some electromagnetic waves reach the Earth and some do not? So that's from Anthony.
Right. It's important that we have multi-wavelength astronomy now. Technologies in the 1930s through the 1960s opened up the electromagnetic spectrum as detection goes. We developed radio, microwave, X-ray, gamma ray, and millimeter sensing methods. They're different from the methods used in a CCD. So we have a whole array of detectors now. And those detectors are, of course, used for terrestrial science of all sorts, not just astronomy. But as far as astronomy goes, the Earth's atmosphere is a very strong filter on the vast majority of the electromagnetic spectrum. So if we take the different regimes, at the high energy end, the X-rays and the gamma rays, essentially as soon as those high wavelength and short wavelength and high energy forms of radiation reach the very upper bounds, the tenuous upper bounds of the atmosphere, 100,000, 150, 200,000 feet up, they start to ionize the gas molecules they run into, oxygen and nitrogen, of course, mostly. And they're and that is so efficient that those high energy waves are extinguished up in the atmosphere, above where all the weather occurs. They don't even get to where the meat of the Earth's atmosphere is. They're extinguished almost utterly in the very tenuous outer parts of the atmosphere. Well, the corollary of that, of course, is that if you want to detect those waves, you can't just be up there in a balloon. People have tried that. You actually have to be above essentially all the atmosphere. So X-ray astronomy started in the 1960s with sounding rockets that were able to go above 100,000 feet for short durations with small telescopes aboard, and that was the birth of X-ray astronomy. And then, even then, people realized, wow, it's not good enough. We need to be in orbit. So essentially, X-rays and gamma rays and ultraviolet radiation, it essentially extends down to about 100 nanometers. You have to be in space, true space, deep space. At the lower wavelengths, at the longer wavelengths and lower energies, it's a sort of different mechanism. It's basically water vapor in large part, or any of the greenhouse gases. So for those longer wavelengths, what happens is their energies are very close or tuned to the spin states, the rotation states, and the vibration states of molecules, which tend to have low energies of transition. And so, and remember that a molecule like water, so just simple H2O molecule, has very many vibration states. The number of possible electron transitions in a water molecule is not vast, but the number of rotational and vibrational states is vast, thousands, many thousands. And many of those vibrational states have natural energies in the infrared, millimeter, and long wavelength regions of the electromagnetic spectrum. So basically, when those waves come into the Earth's atmosphere, they make it through the upper part, but as soon as where they get where the water vapor is, which is the mesosphere, which is where our weather occurs, so 10 to 40,000 feet elevation, they are completely absorbed. And in particular, at the wavelengths corresponding to those rotational and vibrational transitions. But since there's so many of those transitions, it effectively blankets the spectrum with opacity to those waves. What that means is that there are little windows where you can get lucky, where longer infrared waves can get through. So there's a 10 micron window, a 20 micron window, and a very bad window at like 100 microns, and that's about it. And even for those windows, you have to be on top of a high mountain like Mauna Kea, or even higher to do the work. For anything beyond 100 microns all the way out to a millimeter, nothing gets through. The radio waves mostly get through, so from everything from a fraction of a centimeter, maybe 5 to 3 millimeters, all the way out to 20 to 100 centimeters, so a couple of orders of magnitude of wavelength, radio waves come through quite happily. And then again, another problem or a different mechanism occurs. At the longest wavelengths, the atmosphere starts to act like a mirror for the radio waves. They're refracted through the atmosphere, and that leads to them either being trapped or deflected or bounced off the atmosphere. So the very longest radio waves, by which I mean meter length, and typically also have trouble getting through. So that's what we end up with. If our atmosphere were made of different ingredients or had a different density, or if we were imagining doing astronomy on an extrasolar planet with a different atmosphere, the situation would be different.
Right, last question.
All right, so this question comes from Wheeler, and the question is, are type 1A or IA supernova or the same maximum absolute brightness, or do they just have a similar light curve that can be fitted?
That's a good question, because there is a subtlety about type 1A supernovae. The typical, to put a round number on it, the amount of energy that comes out of a type 1A is about 10 to the 51 ergs. That's a phenomenal amount of energy in the detonation of that explosive star. But what was observed, and so in simple terms, that amount of energy is regulated by the physical process that the supernova goes off, the way the white dwarf explodes, to within 15%. That's what we see when we look in regions of space where we know the distance and we therefore measure the luminosity. We see the variation from one supernova to the next is on average no more than 15%. And that's what lets them be distance indicators. But it was also realized in the 1980s that the situation is not quite that simple because, and I think the question is alluding to the fact that the light curve, or the profile of how the light rises and then falls. So to summarize that, basically for the first few days after a supernova goes off, the light is increasing, it reaches a maximum brightness and then starts a slow decline, which of course continues for months and then years and then decades. So the typical supernova is only observable to large telescopes for a few months. The width, you can put a characteristic width on that rise and then decline, and it turned out that that width is not constant from one supernova to the next. And it also turned out that the width of that light curve, if you like, was correlated with the luminosity of the supernova. So what people did was they were able to purely empirically, this was not based on a fundamental physical understanding, as part of the interview I had with Dave Arnett explains, people were able to empirically use this relationship between the width of the light curve and the intrinsic brightness of the supernova to tighten up its use as a standard candle or a standard light bulb, and therefore a distance indicator. It's an unfortunate situation though, because we don't physically understand the nature of this relationship between the luminosity and the width of the light curve. But we use it operationally to create an empirically good distance indicator. Astronomers would be more comfortable if they had a deeper physical understanding for why the light curves vary in the way they do. And that, we hope, will be coming in the next few years. And I think that's our time for today. We are moving the time of the live sessions around from week to week, and that's partly to give people who have schedules that won't let them make one time at least make another time, and we're also varying the time in the day since some people can't do the early evening East Coast time. Next week I have some travel, so I'm fairly certain we'll be on Tuesday, but we'll give more than a day's notice for all the future live sessions. Thank you for participating.